let's say we have an example of this, right? So we would try to solve it manually, okay, like what you have learned, okay, and also we would want you to try to solve it using Ansys workbench, okay. A steel plate is subject to an axial load as shown in the figure. Then we want to approximate or determine its deflection average stress along the plates. So you have a thickness of 1/16 inch and a modulus of elasticity or Young modulus or material properties here is 29 times 10 power 6, okay, pound per inch square. So here is fixed, okay? Here is loaded with the 800 pound, right? So if you go back to it's the basic step of a computation FEA, the computational step, a basic computational step. So here we discretize the solutions, okay, from if we do manually. So first you have to discretize the solution into finite element. And we are looking into 4 elements here, okay. For this problem, we discretize into 4 elements, 1, okay, 2, 3, and 4 at here, right? So we have to assume a solution. So axial loading, if you still remember, we have for one element, we are using this F equals to AE over L. So we are saying that F equals to K delta L itself, right? So we know that our E equals to our stress over strains. Then in terms of stress over strain, we have the F over A, okay, delta L over L, right? FL over A delta L equals to E. Okay, if you rearrange in this form, then we have our F equals to AE over L delta L. So this itself is our so-called K. So this is our K. So in the case of the matrix forms and of one element itself, we also have determined that if you look into this, okay, develop an equation of an element. So our element, let's say we're looking to element, we have 2 nodes, right? One elements, we have 2 nodes. This is, let's say, I, this is J. So our Fi equals to KEQ UI minus UJ. Then we have Fj equals to KEQ, then UJ minus UI. So at the end, in the matrix form, we have this Fi, Fj, okay? Then we have this UI, UJ, then we have KEQ, okay? Then minus KEQ, 2 times 2 is a matrix, negative KEQ, KEQ, okay? So that is our F equals to, for one element, equals to K elements, okay? Then equals to U, okay? So that is for one element itself. Then we have the elements, then we assemble that. Did I show you how to assemble the global stiffness matrix by looking into the diagram? Did I last week? So if you look into this particular problem itself, okay, so we have 4 elements, 4 nodes, okay, we have node 1, node 2, node 3, node 4. So our stiffness matrix, global stiffness matrix, our K itself, G will be a 4 times 4 matrix, okay, because we have 4 nodes. So how to build that 4 times 4 matrix, okay? We know that for me, I mean, you have a K in 4 times 4 matrix, we will have K 1 1, 2 1, 3 1, 4 1, 1 2, 2 2, 3 2, 4 2, 1 3, 2 3, 3 3, 4 3, 1 4, 2 4, 3 4, 4 4. All right. So that is the global stiffness matrix that will be look like. So we have to determine this global stiffness matrix in order to assemble into one problem. Then we solve the entire problems, right? So how to determine this? So we have built into here, right? From here, right? If you can build this out, then probably we can fill in the blanks of this K11, K22, K23, K44. So from K11, we look into the diagonal first lah. So let me change the color. So you look into the diagonal, you see that it's 1, 1, 2, 2, 3, 3, and 4, 4. So here we are looking into how what stiffness is directly connected to the node 1. Okay, K11. What is the stiffness that directly connected to node 2? Okay, node 3 and node 4. So in this case, if you want to find K11, then we are looking into the node 1 itself. What is the spring or the stiffness that is connected? Okay, that is connected, okay, to node 1. So it's K1. So we put the K1 at here. So for node 2 itself, if you look into node 2, you have 3 springs connected to it, K1, K2, and K3. So K22 is K1 plus K2 plus K3. K33 is at node 3 itself, we have K2, K3, and K4. K2 plus K3 plus K4. Right? Then K4, node 4 or K44 here is only K4. Right? So that gives us this. So to determine the rest of it, so it is K12, K21 will be the same. K31, K13 will be the same. K32, 23 is the same in that case. So here how we define, we put a negative for all of them. Okay. Then we find between, you see the 1, 2, between 1, 2 and 2, 1. So it's between, we are saying that any stiffness that connecting node 1 and node 2. Okay, if we're looking into 3, 1 or 1, 3, then any stiffness, okay, that is connecting to node 1 and node 3. All right, so something like this. Is 1 and 2 is connected, okay, by any what spring. 1 and 3 is connected, okay, by one spring. Okay, so that is what it means here. So if you're looking into K12 itself, node 1 and node 2 is connected by K1. So you have a negative K1 here, negative K1 here. 1 and 3 or 3 and 1. 1 and 3 is not directly connected. So, okay, yeah, you have to go through 2. Okay, so no connection or what we call no spring. That basically you have to go through 2, then only you have 3. So here is 0, 0. 1 and 4 also no, nothing. Okay, 1 and 4 unless you have a spring. Okay, a spring at here, connect to here, then yes, this is 1 and 4. But in that case, 1 and 4 directly no. So I erase it. Then 0 lah. Okay. Then we're looking into 3, 2, 2, 3. 2, 3 here we have from 2, 3 we have K2 and K3, right? So we have to put a negative K2, negative K3, negative K2, negative K3. Right? Then we have 4, 2. 4 and 2 also again is 0, 0. 4 and 3, okay, 4 and 3, and 3 and 4 here is negative K4. Okay, so that built us the global stiffness matrix at here. All right. So once we have this, then probably we can compute all the values out lah. We know that K is AEOL, so A for the areas for the first elements is different with the second element and third element. Second and third element are same, okay, area and length, okay, so and material. So probably 2 and 3 are same, K2 and K3 are same, but K1 and K4 is difference, okay. So you have K1, K2, and K4, then substitute everything in, then you build that particular global stiffness matrix. Right, then next is assemble. Assemble, then we have to apply boundary condition and thermal loads. Okay, here is, of course, is a static load lah. Then here, looking into here, the problem itself, okay, we have a load at element node number 4, right? And we have a fixed support at node number, what we call 1. So we are saying that U1 equal to 0 in this case. So instead of 4 times 4 matrix, okay, so we know that the top parts are this K, it can be simplified to 1, 0, 0, 0. Okay, why? Because 1 times U1 equal to 0, then the rest are 0. Okay, so meaning to that is only U1, it fulfill the one condition, which is boundary condition is U1 equal to 0. Okay, then we have this, our force itself is applying at at the node 4. Okay, so it's 0, 0, 0, 800. So if we have simplified this, okay, then U1 we do not need to determine, then we only need to determine U2, 3, and 4. U2, U3, and U4. In that case, it will be the 4 times 4 matrix will be simplified to 3 by 3 matrix. So meaning to that, we only calculate here. Okay, multiply with U2, U3, U4 equals to 0, 0, 800. Okay, solving this using what you have learned manually, okay, either using direct method, iterative method, Jacobi, Gauss-Seidel, Gauss elimination direct methods, okay, or LU, or even you have a matrix form, the inverse matrix to find the inverse of the K matrix, or you have a MATLAB, you have Excel, then you can solve it, okay, to find U2, U3, and U4. So in this case, we solve this algebraic equation simultaneously. We get U1, of course, is 0, fulfilling our boundary. Then U2, U3, U4 is where you solve the 3 times 3 matrix. Okay, the K U equals to F. Okay, this is 3 times 3. This is 3 times 1. This is 3 times 1. So end up you will get 3 times 1. Right, so from there you have the U2, U3, U4, then probably you can find your stress. Okay, we have a E equal to stress over strain. Our stress equals to E multiplied with the strain, and the strain is basically our U2 of that particular element itself is U2 minus U1 over the length of the elements. Okay, right. So you know that the stress of that particular element itself for the first element is 2560, fourth element also at 2560, but then at second and third element is around 3200. Probably is due to concentrations at here, okay, because you have the discontinuity at here, so you induce a higher stress at these particular regions, right? So that is some sort of analysis that you can manually calculate it, right? So if we're going towards this particular Ansys, okay, the same problem, if I want to analyze using Ansys, how you want to do it. So probably you have to follow this step by step later on when you have the access towards the what we call the software lah. Okay, so again you use static structures, okay, then you assign the materials. Okay, so you choose the correct unit first lah. Under units you have to choose the units at here, so easy for you to set lah. So if you're PSI, then you probably you have to set the 2.9 E is a 29, right? 29 E6, right? 29 E6 power over inch square, then PSI is a 2.9 power of 7, 10 power of 7. Right, so you set your correct what we call properties, okay, especially in this case is Young modulus, right? Then you go to geometry. Here we are using a design modeler. So this tutorial or this case study will teach you how to model it in under design modelers. Okay, so step by step. Okay, for that easy, not so complex model. Okay, so once you have done the modelings, right, then probably you can go towards the static structures, or what we call the mechanical. Double click the model, then it will lead you to the mechanicals. So this mechanical where you have to assign your materials properties, then you have to discretize it, then you have to apply the loads, apply the boundary. In this case, no connection because you only have one parts, right? So you have to apply the boundary, which is a fixed support at here, the end, a load at here, okay? Then probably from there, you can get your results. Here is talking about stress, okay? Then yeah, you can get the deformation, you can get the stress, then you can compare the stress levels, okay, by putting a probes on any of the surface. Okay, so this is what I have completed for that particular problems. So you can, yeah, later on do it yourself lah. Oh. So again, if you look into these problems, right? So first you have to go to the engineering data lah. We go according to the flow itself, then structural steel. So if you look into the unit itself, probably inch, then we know that we have set the correct boundary Young modulus 2.9 psi, right? Then it's good. Then you can, this is the steel. Then we move towards the project back. We find the geometry. So you see that here there is a icon DM. So I'm using a design modulus. So if you draw that model it before, then you double click it, it will go towards what we call design modeler at here. Okay, so following that step by step itself, you draw a model, some sort of like that. Oh, a model like this. So I put, actually it's a 3D, okay? So you can draw it some sort like this, okay, with the dimension givens, based on the dimension givens, okay? So once you have draw it out based on what the tutorial, what we call the case study tutorial guided, okay, then you can anytime close this thing, okay? Once you have changed anything, close this thing, then it will lead you to this. You see, so now I open this geometry, then you need updates already. So you double click on this, it will say you change something, you have to refresh, okay? So you from the start, now you become or from the tick just now you have a refresh button. So I double click this model, it will re-import everything towards the what we call the mechanical. So now we are opening the mechanical from design modeler. Now we switch to mechanical. So again, the geometry that you uploaded is the one that we have drawn using design modeler. Okay? So if I click on this is a solid, then it's a structural steel that I have assigned. Okay, I assign structural steel, the one that I have changed to the Young modulus or elastic modulus of elasticity. Then the mesh, okay, of course I can ask it to I can change the sizing. Okay, I change the size. Let's say if you look into the unit itself, you can change lah. Of course, you can change to what that you're familiar. So I put 0.1 size, right, based on the tutorials. Right, then I can regenerate the mesh. So because just now we opened the design modular, so it thought the system thought that we have changed some things. Okay, so you have to re-update everything again. So one is discretize. Then we will look into the support, okay, and also the force that we apply. So the support will be on the entire surface on the right or left. Okay, the force will be at the right here. Okay, 800. So once we have set all these informations, then you see that we can actually run, right? Inserts. We have done, you have tick, you see the green tick at here, okay, or a tick, then probably you can go towards solve, okay? But before solve, you think that you want to call for other, what we call, other post-process result. Then if I want to look into total deformations, I want to look into the stress. That's now we look into principal, maximum principal equivalent stress. Then you want to look into stress to probably the safety factors. Then we can add it to solve. Okay, else you can solve it, then you can call this thing out also can. Okay, so not an issue because this is more towards post processing. Okay, so one is solve. Right, so you can also see the normal stress. So if you want, okay, so that is the stress distributions. So you see the stress distributions of this particular plate itself undergoing a fixed support here, load 800 pound at here. So this is a deformation. And of course, you will see that here is larger, the maximum set here. Then the equivalent stress also some sort of similar compared to normal stress also. Then the safety factor here is again around 5.4. So it's still safe. It won't fail. It won't yield. Okay, in this case, right? Then you can animate it lah. But at this animation basically to show you the difference between when it pull, okay, and release. Okay, that's it. Okay, so you have not so much information at here. Right. So if I want to look into a little bit towards the result itself, okay, so I want to probe, okay, what is the magnitude of here, what is the deformation at this here. I know that maximum is 0.0007 inch, 78 inch. So if I want to go a little bit into where is the maximum, so if I click at here, it will tell me this is the maximum point, this is the minimum point at here, right? And if I want to manually probe it, then probably I will put a probe right here. Then you can see that. Okay? So you click on here, so it will tell you the where is it. Okay? Right. So if I want to look into the stress itself, okay, I will put a probe right here also. So here, what you have obtained just now is 2560, right, at around these regions, right? So it's also some sort of quite close. Okay, 25. Okay. Then if you are in what we call just now we are talking about, if you are in the regions of element 2 and element 3, we manually calculated will be around what did we calculated will be around 32, okay, 3200. So yeah, you can, yeah, it is quite closer if you look into this. Sorry, if you look into this, then yeah, you will have around here these regions around, yeah, 33, 32, yeah. So here also around 25. Okay, so that is where you can put your probe at anywhere that you want, okay, to investigate. Right? So yeah, that is what you can do particularly, okay, for a very simple axial loading device. Okay, so you have all the tick here, meaning all the setup is there, then probably you can do the solutions. Okay, so I will leave it to you. Okay, you try it when you have the access of the software, then let me know if you have any issues.